Assalamualaikum warahmatullahi wabarakatuh to Dr. Ahmad. My name is Siti Nurlina binti Azmi. My matrix number is AE180030. Right now I am going to talk about the overview of our project planning. In our project, it started with the block diagram of the process system, as you can see here, and the process type with total up the industrial load until it gets its power demand. So for the details, we will discuss later on. And for the next step, for the second step, we have to design the suitable industrial network by using the single line diagram, and it will be described more detail later on. And the third one is we have to choose the suitable transformer and cable sizing for each transformer on each division, which the total division got 5 division, including the 60% increment of load, which and also have 5 transformer from T1 to T5. And the all distribution transformer will we decide to put the impedance as 6% and 3-phase load. Last but not least is the environment and sustainability solution. So from all the criteria, from all the load that we have decided, we have to think the best solution for the industrial load to have sustainability in their system. Right. Okay. For the flow chart, we have started with listing out and calculate the given loads from division 1 to division 3, which are the existing load. And next we have to define the load with appropriate active power, apparent power, and its power factor. And next we have to define its utilization factor and also diversity factor for all the different loads. After that, we have to calculate the power demand for existing load estimation. And next we have to divide all the apparent power that we obtain on the system with 65% in order to select the appropriate standard transformer rating that is close to the system in kVA. Okay. After that, if the transformer rating is suitable, we have to proceed with the next step, which are calculating the recommend the cable size. If not, we have to reselect the appropriate standard transformer rating that is close to the system. Okay. Next, we have to calculate and recommend the cable sizing. If this cable is suitable, we have to proceed for the next step, which are designing the single line diagram for the system. And after we design, we have to add 2 division loads with 60% increment of the total existing load, and calculate the new load estimation and its power demand. And we have to repeat the step back, which are to reselect the type of transformer rating that are suitable for additional division, which are the division 4 and 5. And after the transformer is suitable, we have to choose the suitable cable sizing. And then if it is suitable, we have to recreate the single line diagram for all the designated system. And last but not least, we have to prepare the technical report in this design system. So here is the total apparent power of the industrial loads in this factory. The division 1 to division 3 is the existing load of the system, which have induction motor, lamp load, heating and lighting, synchronous motor, MCC1 and MCC2. So for the division 4 and 5 is additional 60% increment from the existing load. So from the horsepower here, we have to obtain the active power in kilowatt, which are the operating, by multiplying the horsepower here with 1 horsepower equals to 746 kilowatt. We have to multiply it with 746 kilowatt, and then we can obtain the output rating here. For all the system load in this factory, we use 3-phase. In order to get the apparent power here, we have to divide the active power with the 3-phase, the square root 3 times 415 volt. And next, this is the given power factor from the questions and the given efficiency. So here we calculate with the power factor multiply with efficiency to get the value. Next, we times the apparent power here with the K here, which are the multiply from power factor and efficiency to obtain the value of total load of power, apparent power. Next is the power demand of estimation load. So here is, you can see here that this is the distribution transformer from T2, T3, T4, T5. 41 is from the main supply. So for the T2 is have the division 1 load, which are induction motor, and this is the active power that we have calculated earlier. And all the motors here actually it will be operated 24 hours a day, every day until at the end of the week. And next, we consider with the apparent power that we obtained earlier here. And next is we have to decide the suitable utilization factor for division 1, division 2, division 3, and division 4. For division 1, the suitable utilization factor is 1, while division 2 for lamp load is 0.9, and heating and lighting is 1 because it operates more. Division 3 is 1, division 4 and 5 is 1. So then we calculate the maximum kVA apparent power for the system. We obtain the value, and then we have to decide the suitable value for the diversity factor in the system. For induction motor, which are lower than 1000 horsepower, we assume that the suitable diversity factor is 0.9, while the more than 1000 horsepower, we decide to put it as 1. And for division 2 is 1. Division 3 is for synchronous motor, the diversity factor. The first diversity factor is 0.9, they are suitable. and also the induction motor, while MCC1 and MCC2 is white. For division 4, the induction motor which are lower than 1000, I lower and equal to 2000, I put it as 0.9, while the higher than 1000 is white. And then for the division 5 is 0.9. And next we can calculate from maximum kVA to with the diversity factor in order to get the value of subdivision board. And next with the value of subdivision board, we calculate times with the suitable diversity factor. For all the diversity factor here, diversity factor for the second one is all the same 0.9, and consider it as a suitable factor for the system. And after that we can obtain the value for subplan distribution board here. And next for the diversity factor KS3, we consider that the suitable value is 0.9, and we calculate from the subplan distribution board with the KS3, we will get the submain general distribution board in kVA. So here we got the value of 7068.99 for 1 kVA. That's all from me.
Assalamualaikum. My name is Nur Ismahani binti Muhammad Jaswadi, and my matrix number is AE10028. For the next, I will continue to present for the design part. So here we have our main supply, which is from TNB grade tenaga nasional berhad, which is at 132 kV. And then the transformer 1 will step down the voltage from 33 kV until 11 kV. And then it will go to the division 1, division 2 and division 3. So this is 11 kV bus bar. First, for the division 1, it will go to the line. The 11 kV will go to the division 1 line. It will go through the circuit breaker first. The function of circuit breaker is to protect the line from trip or any fault. And then the transformer 2 will step down the 11 kV to the 3.3 kV, and then it will the voltage will go to the different load at the line, which is here we have induction motor at 400 horsepower, and second we have induction motor 2 at 1000 horsepower, and then we go to induction motor 3 at 1500 horsepower. All of these three have the power factor different and efficiency different. Next, the 11 kV bus bar will go to the division 2. First, it will go through the circuit breaker, and then we go through the transformer 3, which is the transformer 3 will step down the voltage from 11 kV to 0.51 kV. And then here we have the load 1, which is lump load at 100 kV kVA, and then here we have the heating and lighting at 30 kVA. Okay, next, the 11 kV bus bar will go to the division 3. Okay, here at division 3 we have two transformers to step down, which is T4 and T5. So first, at the transformer 4, we have the 11 kV until 6.6 kV step down voltage. So here we have only one load, which is synchronous motor. And then in the 6.6 kV bus bar, we go to the step down transformer 5, which is it will step down the voltage from 6.6 kV until 0.51515 for 6.6 kV until 0.415 kV, which is at here we have about 3 load, which is MCC1, which is 450 horsepower, and then we have induction motor at 250 horsepower, and MCC2 we have 250 horsepower. So this is that's all for this system. Okay, next, this is the design for the load, which is happen to have 60% increment. So here we only add the transformer division 4 and division 5, which is we have transformer 6 and transformer 7. Okay, that's all from me. Thank you.
Present for the project outcome and discussion for transformer sizing calculation for criteria 1. Okay, table shows that the variable transformer rating selection discrepancy resulting from different voltage value for selection reason. Transformer rated at 16,000 kVA and 7,060.99 kVA were chosen for distribution transformer T1. And for transformer 2, it's rated at 4,000 kVA with a maximum output of 2,461.5897 kVA. Transformer 3 rating is 1,000 kVA with a maximum demand of 513 kVA. 1,600 kVA with a top total maximum demand of 937.3634 kVA for transformer 4 and 5000 kVA with a total maximum demand of 3007.5898 kVA for transformer 5. The transformer rating are also displayed in this table. Okay, for our cable sizing, we choose the cable type of XLPE, EPR. Cable material is copper. Final temperature for this cable is 250 degrees Celsius and the initial is 90 degrees Celsius. The cable constant is 143.08. For clearing time, we use 0.2. Okay. For division 1, 2, 3, 4 and 5, we calculate the maximum load per feeder. Okay. For division 1, the max load per feeder is 2646.79 and the current per feeder is 0.46306, and we choose the size of cable. The size of the cable that we choose is 185 millimeter per square. And for the division 2, we choose the size of the cable is 240 millimeter per square, and for division 3 we choose 400 millimeter per square, and transformer 4 we choose the size of the cable is 185 millimeter per square, and lastly for the division 5 we choose the size of the cable is 120 millimeter per square. That's all.
Hello, Assalamualaikum. I am Fazali Kenanan. My metric number is BEV40203. So now I will explain about the environment and sustainability in design issues. So in this era, manufacturing industry in Malaysia as one of the income that will have many goals. So it is important to see the environmental and sustainability in the electrical network in the manufacturing industry. So most of the industry consists of the petroleum, chemical, rubber and plastic products for 23.8%, and electrical and electronic product for 16.6%, and food, beverage and tobacco product for 4.6%. So this is all the manufacturing industry in Malaysia. By step in the processing of their materials, and some of the design in electrical networks may have flaws during the manufacturing process and may impact the environment in negative ways. So one of the design issues for the electrical distribution system is the performance of inductance motor that is generally used in all the industry. So the inductance motor may cause the energy waste and cause thermal pollution. This is depend on the efficiency level and oversize level of the induction motor used for the specific application in the industry. So the thermal pollution will occur when thermal energy is directly used in the preparation or treatment of materials in the manufacturing, or when the water from the public grid is used in the process and typically disposed into the sewage system as water vapor to air. So the wastewater will become hotter than the water body's original temperature. So the high temperature will reduce the oxygen and will cause problem to the aquatic life. So the electric motors also use estimately 45% of total electrical energy consumption. So choosing the most efficient electric motor or increasing their performance will help in energy conservation. So in 2009, the industrial sector reckoned for 43% of the total energy consumed, and demand for electricity is anticipated to increase from 91,539 kilowatt hours in time 2007 to 108,732 gigawatt hour in 2011. So the performance of inductance motor should match its certain application to ensure the efficiency of the electrical usage. So another design issue in the electrical distribution system proposed is to maintain the high level of stability and quality in the electricity supply after adding two divisions, which is division 4 and 5. So after adding the division, the amount of inductance motor increased, resulting in increasing of electrical usage. So the electricity security is used to maintain continuous electricity availability by enduring and recovering from disturbance and contingencies. So this system is required to ensure that there is no problems during working hours, and any waste removal facility can continue to operate to avoid any risk in environmental pollution. So now I will explain about the environment and sustainability for solution. So the most common electric motor used in industrial settings are reverse induction motors, particularly for pumps, fans, compressors and conveyors. Electric motor energy losses can come from a variety of different causes, including friction, loss of kinetic energy in electric motors, and resistance losses. Considering environmental factors when selecting a motor for a specific application can result in significant energy saving over the motor service life. So the motor load index is introduced as a quantitative method of evaluating the various oversizing level. So this is the formula for the motor load index. Motor load index is equal to B mechanical power requirement and rated power motor selected. Furthermore, to see the performance of the motor cooling system that has been affected, we need to check it regularly. So to accomplish this, you can clean the motor surroundings on a regular basis and look for any potential air blockage that may be flowing onto the motor frame and related parts. This can help in preserving energy and reduce waste by increasing the performance of the electric motor. So for the next issues, we use the ADA application in helping to maintain high level of security and quality in the electrical supply. So the ADA is an integrated monitoring system that enables distribution system operators to keep an eye on the any problem on the grid in real time and automate network reconfiguration to improve the effectiveness of power delivery. And this can help in minimize the power loss and increase the electrical system performance. This can also be further improved by using renewable energy as emergency electrical supply sources such as solar energy and hydropower. This can help in increase the efficiency of energy usage and avoid the risk of environmental pollution.